about what is Plonky3 at the first place, and we'll start off with a demo on how to prove the addition of two numbers and how to generate a proof for that and verifying with the final number. Let's go ahead. Yeah, I'm Ganesha everywhere, Twitter, GitHub, etc. So yeah, Plonky3 is a toolkit for implementing polynomial IOPs such as longs and stars. Built on the principles of stars, it combines techniques from stars with polynomial commitment schemes like FRI to offer fast and succinct proofs without requiring a trusted setup. You can build ZK VMs with more modularity with the available hashes, available fields as per the requirements of its components. So let's start off with a basic example of generating a proof for addition of two numbers and verifying it with the third one. What are the steps involved in this? How do we start? So the first one is define the computation. What exactly is your computation? In this case, we have a plus b equals to c. Define the constraints. Constraints are basically rules which should be followed by each step of computation. And then we have execution trace, that is step-by-step states of computation. You can count it as if there is a matrix. Each row of the matrix is counted with step, and each step should follow the constraints that is given set up in the algebraic steps. And the last, not the last, but the penultimate one is choose your hash and fields. We have number of hashes supported, that is break 3, Poseidon 2, etc. We also have multiple fields that has been supported, that is Morrison 31, Goldilocks, and Baby Bear. And the last step is generating proof and verify. These are the basic four steps you need to follow for any program, for any computation that you want to prove and verify. And yeah, let's go. I'll start off with importing Plonky3 libraries and different fields. So yeah, the first step is defining computation. That is what do you want to exactly generate a proof for. And the second step is basically writing your array scripts. So in this case, you are writing rules such that local 0, that is the 0th column, and the first column should add to be equal to the third column, that it should be asserted to be equal to third column. Are you able to see it? Or should I zoom in a little bit more?
Nice. Oh, too big.
Yeah. So this is our constraint, this is our test script, and then we define our execution trace. So in this case, we are using FRI, a commitment scheme, which has circle PCS, which underline uses matrix having at least 4 rows. So it won't work if you just push one row and and work on it and generate a proof for it. So let's suppose in this case we only have one row. So what you need to do is you need to pad it with zeros so that you fill up all the 4 rows, and at the end you will get a 3 cross 4 matrix. So in this case you can see these are the ABC values that we are filling up in the first row, like this. So this is just a vector right now. We are not formed a matrix yet. This is just a vector, and then we are padding with zeros in all the 3 remaining rows. So yeah, again this is just a vector yet, and then we form a matrix here. We print it so that we come to know how exactly it looks like, and then we form a matrix using that vector that we have just created. That's about the execution trace for this example. And these are just a basic setup for any Plonky3 computation that you want to do. Like you have to define your hashes, define your fields. So in this case, we are using Mersin31. So we'll be using we just we are defining the type aliases, and we have here the byte hash. Again, this is the type aliases, and we are using kcheck256 hash field. And so these are just the basic thing that you need to do for every computation. And we are creating a config here, that is a start config with the TCS challenge and challenger. We are defining the variables, that is we need to prove 4 plus 5 is equals to 9 in this case. And again we are initializing the AS script, initializing the execution trace, and initializing the challenger as well. And now we generate a proof using 5 of these things, that is challenger, config, AS scripts, trace, and vector. Then we basically have a challenger. Challenger is basically when a challenger interacts with the prover to send some randomness during each step, so that it does not have a proof generated already, that is let's say it's not using pass-through, so it is verifying, the challenge is verifying by interacting with the prover again and again by sending some randomness, and the prover is basically sending proofs for all that, and so that there is no edge cases that are remain behind when the proof is generated. And lastly, we verify that proof. So let's go ahead and run this. We are successfully verified. Let's see the matrix here. As you can see, it's a 3x4 matrix, or I should say 4x3. I'm not sure. Is it RC, right? So it's 4x3. My bad. So it's a 4x3 matrix. We have padded with zeros and in the last 3 rows, and the first row is basically our numbers. Let's also verify with some other numbers. Let's try some. Left is not equal to right. Constraint. Again, it failed because the numbers are not equal. That's it for the demo. I might take also another demo someday about Fibonacci, like proving the Fibonacci sequence, and writing execution trace for it, writing AS scripts for it, etc. I have pushed this in GitHub. I can send this over the call.
You can send learning share. Link share.
Okay, sure.
Did you send it?
No, okay, I just send it right away.
On top.
Okay.
Higher.
Thank you. Learn and share.
Thank you.
Do we have any questions? Thank you.